14.2, we talk about limits and continuity. Now we have two functions, right? So we have this function and this function. Okay. I also gave you the graph for the two functions. Okay. So I use the graph from graphing F to graph the two. This is the graph for F, this is the graph for G. Okay. We can visualize it in 3D. So when X and Y both approach the zero, what does the F of X, Y approach to? So in other words, that if you think about it like a fish, it's swimming towards the 0, on this xy plane, but it has to be along this swimming toward the 0, but then we go along this surface. Okay. What do you think about the function value is approaching to? So we go this way, it can go swimming this way, or it goes swimming this way. But eventually, no matter which way you approach to 0, no matter how this xy approaches 0, no matter which path you take, as long as you go along the surface, looks like they all end up over here, isn't it? Okay? So doesn't matter which way you approach it, it still ends up over. The function value is going to be very close to this point of the whatever the z value over here. Okay. Notice that this function here is undefined at 0, right? Notice that x and y, when x and y equal to 0, we are dividing by 0. So 0, is actually not in the domain of function. So this should be empty. There should be empty hole over here. So there's a hole over here. However, it doesn't matter how you approach the x and y approach 0, as long as you go along the surface, you're going to get arbitrarily close to this point. Okay. So this function is going to approach to 1. So it looks like it is a 1 here, the function value. Okay. How about the second one? Well, is this function here, is it defined as 0, 0? Is 0, in the domain for the function? No. Yeah, it's going to make the denominator equal to 0, right? So we should have a hole over here in the graph when x and y equal to 0. A hole. Okay. Maybe even my mind that is mistake like it. Okay. So what happens if you go approaching when x and y approaching 0? Maybe along this x-axis, you're looking at over here. Looks like it approaching to 0, right? But what about another way? So what about if I'm approaching 0, along the surface and then along this y direction? What do you think? It doesn't look like it's approaching 0. It looks like approaching to a number up here, maybe 0.5 or some other number, right? So if you approach 0, along this direction, I've got a number. But if I approach 0, along this y direction, I've got a different number. Now, does it remind you of the left-hand limit and right-hand limit? Right? So remember when we do the function of one variable, when the left-hand limit and right-hand limit do not agree, what do you say about the two-sided limit? When left-hand limit and right-hand limit do not equal, then the limit does not exist. Okay, so over here, this is actually the example that is for function of two variables. So if you approach this way, you get a different number, and you're approaching this way, you got a different number. Then the limit of this function when x comma y approach to 0, 0, that's not exist. For that one. Okay, now maybe we can use a table. Remember, we can start a function by table, right? Okay. The first table over here is the table. Those are for the values of f of x comma y. Okay. That was, let me write down that. What was the function, right? Take a look at the table and see what you observe. What was the function there? F of x comma y. That is, let me write it down for you. So f of x comma y, that's equal to sine of. Okay. So that was the first function that we have. And then what we do over here is we make the table, okay? So this is for different x value, this is for different y value. And then we substitute different x and y value into the function, and then we calculate the function value. Notice that when I have, okay, so y here, I put value, those are less than 0, those are bigger than 0. But when the y approaching 0, from this side and this side, okay? And then over here, f is going to be approaching 0 from here and here. But let's think about what happened to, what value here do you think is going to go to? Yeah, you just say 0, right? Okay, what's your name? Is it Harry? What's your name? Anyway, okay. Alright, so sometimes with the math is very hard to know this. Okay. So you just said that it is, what number do you think here? If I keep the y here to be 0, then let's keep the y here fixed. The y here will be 0, right? So for all this column here, the y here will be 0, and then so the y here will be 0, and then the x over here, you're going to pick different x. X to be negative 1, negative 0.5, negative 2, and you get those values here. And then pick the x to be 1, 0.5, and 0.2, you get those values here. So the x over here is getting closer and closer to 0 from the right side, closer to 0 from the left side. So, and then you see what happens to the function value. When you keep the y fixed to the 0 and x approaching 0 from both sides. What do you think? Do you see the chart over here? What happens? Getting closer and closer to what number over here? What do you think I should put? Zero. 0? What do you see here? Yeah, so I say 1, right? So 0.8, 0.99, 1, right? And then here 0.8, 0.991. And as the x here approaching 0 from the right and from the left, you see the number here and getting closer and closer to 1 from this side and also from this side. So it should be, maybe it should be a 1, right? And then second one here, you can keep this x here to be 6, to be 0, and you let the y approaching 0 from this side and this side. Now, looks like the function value is getting closer and closer to 1, right? And here you get closer and closer to 1. So I think 1 is the reasonable choice for that one. So you see the table here. So, yeah.
But if that's your function of x, if your function is 0, if it is 0, like approaching 0, or are you talking about is it approaching 0 or it is 0?
We are talking about x comma y approaching 0. Okay. So
it is 0, it'd be undefined.
Yeah, it is undefined. So x comma y approaching to 0, 0. And we want to see what this one here is approaching to. So what does it approach to? So as x comma y approaching to, I think I have this. Okay, I'm trying to fix this. So you see that what are we interested in? We're looking for x comma y approaching 0, 0. And what is the function here? The function y approaching 2. So you keep the x here fixed to be 0, and you let the y here vary. So the y here approaching to 0. Then you see that it's going to approach to 1. And then here you keep the y here to be 0, and you let the x here vary. And you see that it's also approach to 1. So 1 is actually a reasonable number that you take. So for the limit of this function as x comma y approaching to 0, 0, right? It's by looking at the table over here. Okay. Okay, now what about the second one? Well, the second one over here is, let me write down the function. That function was g of x comma y, which is x squared minus y squared, x squared plus y squared. Again, we're going to make the table this way. So first one, I'm going to keep the x here fixed. Okay. Remember, we're trying to take this, we'll say as x, y approaching to 0, 0. And we want to see what does this one here approaching to. Okay, approach to what? So we're going to keep one of the component, one of the coordinate here fixed. Okay, say let's fix the x here to be 0. So we're going to fix the x here to be 0, and then we let the y here approaching 0 from the left and from the right. What do you think, if I think about that way, what number you think I will put over here? -1, right? So we'll say maybe I should put a -1 there. Okay. So maybe I should put a -1 there. Looks like this one is -1. Okay. Now the second time we do here, we're going to fix this y here to be 0, and then we let the x here approaching to 0. So let's fix this y here to be 0, and then we let the x here approaching to 0 from below and from above, right? So if you're going this way, looking at the chart, what number do you think I'm going to put? We should put over here. 1, right? And then you say, okay, that way it should be a 1, right? So if you're approaching, so you have two different approach, right? But then the able to have different number right here. So what do you think about the limit? Does not exist, right? Remember we talked about in the past we talked about limit when you have the left hand limit and right hand limit, they do not agree, then the limit does not exist. So this is a very similar situation here when you fix one coordinate and then you let the other coordinate approaching that, you get different number. You have different approach, you end up with different limit, then the limit does not exist. Okay, so the limit does not exist. What about the first one? The first one looks like should be a 1. The second one does not exist. Okay. Okay. Now someone say, can I try to visualize this? Yeah, I was trying to graph it so that we can visualize it. So the graph of this function is this one. So it doesn't matter how x, y approaching 0, 0, as long as you swing a chord along the surface, eventually it's going to swing close to this one right here, which is 1. The y coordinate, the z coordinate will be 1. Okay. Now, comparing to the graph of this is different angle of the stem, the graph of the stem function here. So if you go along this way, and then you see that it actually goes to different number right here, and you go this way, and it actually approach to different number right there. So if you have different approach, then the limits are different, then this limit here does not exist. Now, in the past, we have only left hand limit and right hand limit. This one here, you can have infinite many approach, right? How many ways you can approach your commutator? You can go this way, right? You can actually not just straight line, you can actually swing like this, right? You can go in curve, okay? As long as you get closer and closer to that, okay? So you have different approach, infinite many approach to that. You can make a parabola approach, okay? And you can make a straight line approach, you can make any kind of approach, like a sine curve approach. And if the limit here, if you can find two different paths that the limits are different, then the limit does not exist. Okay. As long as you can find two different paths that the limit are different, then this limit here does not exist. Now, what is the, okay, this notation over here is to indicate, so what's this notation? Well, this notation is still on the notation for the limit. Remember in the past we just have the limit of f of x as x approaching to a. This is equal to L, right? But now we have function of two variables. We just need to add, instead of x, here is x comma y, and then x comma y approaching to a comma b. Okay? So approaching to this. Notice that how many ways x comma y can approach to a comma b? Not two. Infinite many ways. You can go to that point, right? Think about a point here, a comma b, on the xy plane, right? You can go this way, right? Here, pick a point, a comma b. Then you can go that way. You can go that way. You can go that way. You can actually go legal and then approaching that point, the same point. So you can have infinite many paths to approach that point. Okay. As long as the path stay within the domain of the function. Okay. Now here is the, remember the, do you guys remember? This is for the sigma delta definition for limit. It was a little bit more rigorous at that time, and some instructor actually skip the sigma delta definition for limit. Just try not to scare you guys. But this is the definition for the limit using the sigma delta notation. And what does it mean? Right? It just means that if the x and y, if this one x comma y, if it's close to a comma b, it means delta distance. Okay. Then, actually, let's think about the goal here. So what do we want? So this one says that if you want this to be close to this number, okay, for any sigma, for example, if you want this to be within 1 unit away from this number, then the one here is the sigma. Okay. So you can choose a delta, okay, the delta over here. As long as this one is within delta distance away from this a comma b, then this is going to be sigma distance away from this L. Okay. So let's try to think about this. So you have a comma b right here, okay, and this is a point over here. And if it's within, I don't have different color today. Okay, so if it's within sigma distance away from this point, then the output, then this f of x comma y is going to be within delta distance away from L. Okay, so it's going to be within delta distance. How should I say that? Well, think about this is on the xy plane, right? So this is on the xy plane, and this xy plane over here. So xy plane, and this is for f of y, and that's a z. So over here, if you take this, a small disk over here, okay, center at AB, and if you make this disk, the radius to be small enough within sigma, then what happens over here in the graph over here? Then the function value is going to be very close to this L within delta distance. But it's a little bit hard to digest at once when you have all those locations. But it's I think a lot of students get scared by all those sigma and delta. But don't be too scared, and I'm not going to test you guys on this. And you can just sit down and think about what that means. Okay. Now, other notation for this limit in this definition here is this. So instead of putting this xy approaching to A and B, you can put this way. X approaching to A, y approaching to B, that the limit is L, or you can put it this way. So those are different ways to write this stem limit over here. Okay. Okay, now let's think about that was like the function of one variable in the past, right? We know that if the left hand limit and right hand limit do not equal, then the limit does not exist. You guys just talk about that. So it does not exist. And now for function of two variable, then the situation is not as simple as this, because it's not just left and right. You can approach to this A and B different ways, just as I said before, right? You can approach it this way, this way, this way. You can actually wiggle as long as it's within the domain of the function and approaching this way. Okay. You can approach it like along a parabola, okay, or along some other graph. Okay. As long as you are approaching to this, then you want the limit always equal to the same number in order for the limit to exist. If you can find at least two different paths that the limit are different, then the limit does not exist. Okay, here's the important part here. Okay? So if the limit exists, then f of x comma y must approach the same limit, no matter how x comma y approach A and B. So no matter how think about the fish, right? No matter how you swim toward this A and B, as long as along the surface, eventually it should end up at this very close to the stem point, okay? Arbitrarily close to the stem point. So here's things that will help you with the homework. So if you find f of x comma y approaching to a limit, say L1, along a path, and then later on you find another path that f of x comma y is give you the limit of L2, and L1 and L2 do not equal each other, then the limit does not exist. So to prove the limit does not exist, you just need to find two different paths that give you different limits. Okay, let's try one example here. Okay, it's a little bit harder because it's very different from the case that we have. It's not as simple as the one that we had before.
So this function here, isn't that the function that we just talked about, right? At that time we used the table, okay? But now let's just use some algebra maybe, okay? So let's approach 0, 0 along this x-axis. Along the x-axis, which coordinate will be 0? The y-coordinate will be 0, right? So here the y will be 0. So if you fix this y-coordinate to be 0, and then let the x here vary, we're going to replace this y here by 0. So f of x, 0 equal to what? What does this simplify into? Equal to 1? Yes, you got it. Okay, that's equal to 1. Okay, so it's always 1. So along this x-axis, the function value is always 1. So therefore, f of x, y approaching to 1 as xy approaching to 0, 0 along this x-axis, because the function value is always 1 along this x-axis. So that should be 1 over here. Okay, so along the x-axis is always 1 right here. Okay, so that is one path. Okay, so you approach 0, 0 along this x-axis. The next one here, let's approaching 0, 0 along the y-axis. So along the y-axis, then x will be 0. So what does the function simplify into? Negative y squared over y squared, okay, which is negative 1. So along the y-axis, it's always negative 1, the function value, right? So the function is going to approach to negative 1 as x, y approaching 0, 0 along the y-axis. And you see over here, okay, it's always negative 1, okay? Now, I'll try to put a 3D picture here. So along this x-axis, it's always 1. Along the y-axis is always negative 1, so down here. So now we have two different paths that give you different limit, okay? So along this x-axis, it goes to 1. Along the y-axis, it goes to negative 1. Therefore, what's the conclusion for the limit of the function as x, y approaching to 0, 0? Does not exist. Yeah. So as long as you can find different paths that give you different limit. This one here, well, that was a little bit different from the one that we have before. Before we only have left hand limit, right hand limit. Now you can have limit from different paths, and they all have to go to the same limit in order for the limit exist, right? But there's something that is very similar to what we have as calculus 1. The limit of x as x, y approaching to a, b is equal to a, right? So x, y approaching to a, b, then x has to approaching to a. Do you agree? Okay. What about this? This approaching a, b, then y has to approach to what? B, right? Y has to approach to b. So the limit of this y is equal to b, equal to this b here. And the limit of a constant, the c here stands for constant. The limit of a constant stay as the constant. So this is the 3 limit, okay, which makes sense. And also the squeeze theorem. The squeeze theorem also holds for limit for function of 2 variables, okay? Do you guys remember the squeeze theorem? I put the squeeze theorem here just to remind you guys. So in the past, we talked about the squeeze theorem. It says that if you have this function, think about this function g of it's squeezed between this function above and this function below. when it's near A. So we don't care what happened if it's further apart. But near this A, this G is going to be squeezed between this F and also the H in between. Then what happened here is if the limit of this function above and the function below, when x is approaching A from the left and from the right, if they have the same limit, if the function above and below have the same limit, then the function that is being squeezed between them is going to force at the same limit at A. Okay, that's the squeezing. The squeezing over here is also called the sandwich stream because it looks like a sandwich. So this function here is the middle layer, and this is above, and this is below. So as squeeze it is more painful, but what's called sandwich stream is yummy, right? And there's also something called pinching stream. So it's pinching again. There's also another name for this. It's called the Promethean. Okay, I also call the Promethean. So this is a police officer, and this another police officer escorting this junk. This people with junk. Then escort this person into the cell. So the junk is like he's wobbling, right? He's shaking. But as long as the police, this one above and this one below, enter the shell, there's a jump here, it has to enter the same shell. So it's also called the police. So that motion squeezing we talk about in 110A. Okay. And the squeezing here also applies to function of two variables. So you just need to add here f of x comma y, g of x comma y, h of x comma y. If this function here and this function approach to the same limit at a comma b, then this has to approach to the same limit at a comma b. Okay. Now, because of the theme here, this three theme over this three equation over here, we know that later on we can talk about what type of function will be continued. Okay, what's the definition for continued? Do you guys remember? What does it mean for a function to be continued at A? Definition of a function f is continued at A is if the limit of f of x as x approaching to A is equal to f of A, which means you can do a direct substitution. Okay. Then the function f is continued at A, if this one holds. So this definition for continuity for function of two variable is very similar. If the x comma y approaching a comma b, and if you can do a direct substitution, a comma b that's equal to this function value, then this function is continued as this a comma b. So that's the definition. What's the intuitive meaning of this continuity? Okay, so that means that if x comma y, if it change a small amount, then this is going to change by a small amount. So in this case here, if x change a small amount, then the y value here changes a small amount. Okay, but then similar for this one right here. Now remember for continue for function of one variable, at that time we say that something like this, it has a gap or hole, then that's not continuous, right? That's not continuous. Similar for that one, right? So the graph of the continuous function will have no hole or no break. So if you have a hole in the surface or a break in the surface, then that function is not a continuous function. Okay. Another one, you can use a sum law, difference law, product, and quotient law. And also you have continuous function. A continuous function will be continued on that domain. Okay. All those laws here for limit here also hold for function of two variables. Now, what type of function are continuous? Do you think polynomial function will be continuous? For one-dimensional case, in the past we talked about that polynomial function will be continuous, right? This one here, function of two variables, this is polynomial in x and y. This type of function will be continuous on R2. What's the reason? What's the reason those will be continuous? Polynomial function? Because there's three equation over here. There's three equation here. So there's three equation over here. A polynomial function built on power of x and power of y and also constant, meaning those coefficients, etc. So because of this, you can prove that polynomial function are continuous. So over here is polynomial function of two variables. So we know that it's going to continue on R2, right? What about this? Is this a polynomial function? Isn't it? No. Polynomial function, the variable will not be in the denominator. Okay, so this is not a polynomial function. It is actually a polynomial divided by a polynomial. Okay, it's a ratio of polynomial. That's called rational function. The polynomial divided by polynomial, those are called rational functions. Just like integer divided by integer are rational number, polynomial divided by polynomial will be rational function. And it talk about rational function. Actually, it's going to continue everywhere except for everywhere in that domain. Okay? If it's not in the domain, then it's not continuous. So here's what it says: all polynomials are continuous, and rational function will be continuous on its domain. Okay? Because it's a coefficient of continuous function. So there are two things that we learn. Okay, polynomial function is continue on R2. Rational function will continue on its domain. If it's not in the domain, it's not continuous. Okay, let's take a look at this one. This one here, looking at this function here is what kind of function? Polynomial or rational? It's a polynomial. Okay, so it is continue everywhere. So we can find the limit by, if it's a continuous function, then we can find the limit by direct substitution, right? Okay. So I'm going to do the direct substitution. Do the direct substitution here. Then we can find the limit. All you have to do is just substitute to find the limit. You get 11. Okay. There's another thing here. In the past, we talked about composite or continuous function is also continuous. Right? So if you have f is continuous, g is continuous, if you compose them, then the result here will also be continuous. Okay. Function of three or more variables. Okay, let's try this one. Here, well, looking at this definition, do you see the similarity between this one and this one? Yeah? You all have to do is just add more components, right? Just add more components. But you take it out. Okay. So that's the definition for function of three variables. And the sigma and delta definition, don't worry too much about the sigma and delta. Okay, think about that. Okay, take a look at this function over here. What kind of function here? Is it polynomial or rational? It's rational, right? So it is rational function. So it should continue everywhere except those not in the domain, right? Okay. So what are not in the domain? What will make the denominator equal zero? Yes, you got it. Okay, so that's equal 1. So when x squared plus y squared plus z squared equal 1, then you have 0 in the denominator, then those x, y, and z will not be in the domain of the function. Okay. But looking at this equation, what kind of surface correspond to that? I heard something. What did you say? It's a sphere. Okay. So Benji just said that it is a sphere. So it's a sphere with center at where? At the origin, and then with the radius to be what? 1. So this function is going to continue everywhere except on the sphere with center at the origin and radius 1. So imagine in R3, right? The function is continue everywhere except you take away the sphere. Okay, you take away the sphere, that's where the function is not continuous. Okay. All right, so next one. Oh, that's all. Wow, we've done it. So the continuity of function, okay, it doesn't matter this one here is like 2 variables, 3 variables, okay? So suppose this is only 1, you have this, then f here is continue at A, and if it has 2 variables, then you have this. So you can use this vectorization example that variable. Okay, that's the end of 14.2.